developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
So when engineers are designing new propellants, they worry about performance characteristics like ballistic properties like burning rates. But they also have to worry about mechanical properties. A crack in a propellant could have catastrophic consequences. So in this project, we're extending our prior work where we have developed ballistic models to include mechanical properties as well. Our ultimate objective is to provide tools to formulators so that they can accelerate the design of new materials.
In the first phase of this project, our efforts were focused on curating an existing database of solid propellant mechanical properties from a different project. In over half of our digitized sources, we found and corrected errors and inconsistencies, creating a database that is both easier to use and more realistic to actual experiments. This improved database was then used to create models for the prediction of mechanical properties such as ultimate stress, strain at break, and stiffness. These models consider not only formulation and microstructure, but also processing conditions, temperature, and strain rate, which are essential to capturing material behaviors. These models were bundled into a graphical user interface along with existing burning rate models to give formulators an easy-to-use tool for quickly predicting propellant properties.
Collection of mechanical property data for energetics is important for understanding a system's behavior throughout its life cycle. However, development of new solid energetic formulations often focuses on obtaining specific performance properties with little consideration of mechanical properties until later in the development cycle. Additionally, collection of high-fidelity data is often a lengthy process and requires significant amounts of material, which makes the traditional research process time-consuming and resource-intensive. Having a predictive capability to guide formulators earlier in the development cycle will be a valuable addition to the Air Force Research Laboratory's toolbox. This tool will complement the development of new formulations, reduce the number of iterations to obtain desired mechanical and performance properties, and continuously improve its predictive capabilities as new and historical data is incorporated into the model.
To help meet the needs of our AFRL partners, we've spent this increment of our AFRL Hub Midwest contract developing a formulator assistant that simplifies interacting with our predictive models while empowering advanced users to integrate them into their workflows. The core interface is an intuitive experience for exploring individual formulations. Users can simultaneously view predictions from multiple property prediction models, facilitating rapid comparative analysis. Formulations can be loaded either from local files or databases that are attached to the models. Additionally, the system presents results from the most similar known formulation, providing valuable context to users. This interface is also accessible via robust command line interface or REST API, catering to users who prefer programmatic access and integration. Once a promising formulation is identified, it can be easily saved or transferred to a dedicated analysis tab for further inspection. The Trends interface allows users to sweep specific inputs, giving useful insights on how formulation adjustments can influence performance. The Sensitivity interface shows users which input parameters have the strongest effect on model predictions for a given baseline formulation. This analysis can help identify which components are more or less critical to final performance. And our Optimization interface goes a step further in examining ideal formulations for use. Here, we can set an initial base formulation, then specify what components of the formulation we are willing to change and within what ranges. Then, we set both our target, which we can minimize, maximize, or find a specific value of, and our constraints, which can use predictions from other models to ensure the optimization of one variable, such as burning rate, doesn't have disastrous outcomes on another, such as maximum stress. Regardless of the interface used, all visualizations will update automatically as you change your input parameters, whether that is the base formulation, the inputs, or the outputs. This allows for rapid experimentation and fosters an iterative learning experience for optimizing formulations and understanding model behavior.
The final major functionality for the Formulator Assistant is an optimization with active learning. Within active learning, the user will specify the range of formulations he wants to explore and an objective function, whether it is to maximize performance or minimize uncertainties. The model will then suggest what formulations you should try next, and you go to the lab and add those to the data set. Even if the first predictions are not accurate, the model will get better and hone in on the formulations that actually maximize or minimize the objective function. This takes our model to the next level and will help accelerate the design of new propellants. We're excited to continue working with AFRL partners and transfer the technology that we develop at the university and put it in the hands of DoD employees.